Ports are tempting places to stage the green hydrogen transition. They are industrial, they move energy, they can handle hazardous cargo, they have deep logistical DNA, and they sit at junction points between continents, supply chains, and industrial clusters. If you wanted to take hydrogen from a decarbonization idea to an industrial reality, a port would be one of the first environments you'd choose. The port of Antwerp-Bruges embodies that logic. It has petrochemical assets, storage capacity, shipping lanes, pipelines, power access, and a large industrial hinterland. The pitch is elegant. Import low-carbon hydrogen and its derivatives from around the world. Crack or electrolyze it locally, distribute it inland through pipelines or vessels, and feed it into the industrial and maritime systems that already rely on fossil molecules today. On paper, the match looks perfect. But hydrogen at port scale comes with a trap. The trap is not technology failure, and it's not lack of ambition. The trap is overdesign. Ports, by their nature, dislike being constrained by future uncertainty. They do not know which hydrogen vector will win: ammonia, methanol, liquid hydrogen, e-fuels, or compressed gas. And they do not know how quickly demand will ramp in shipping, industry, or mobility. So they hedge by trying to keep all doors open. They build for ammonia just in case, for methanol just in case, for electrolysis just in case, for CO2 network compatibility just in case, and for bunkering standards just in case. Each just in case adds CAPEX and redundancy. Each redundancy raises the cost per kilogram of hydrogen that early off-takers will face. The more vectors a port tries to support before demand is real, the more it amplifies the cost of balance of plant, storage, cracking, safety, and utility infrastructure. Before anyone realizes it, the electrolyzer, the part everyone debated for years, becomes the least important cost driver in the system. Look at Antwerp-Bruges through that lens and the whole story shifts. It is one of Europe's busiest petrochemical nodes, handling large volumes of ammonia, methanol, hydrocarbons, and gases. It already stores hazardous cargo at industrial scale and connects to an inland network that feeds refineries, chemicals, and heavy manufacturing. That industrial logic makes it an attractive candidate for green molecules. But to become a hydrogen hub, it must simultaneously operate as importer, converter, producer, bunker supplier, and inland distributor. Each role has different technical requirements. Import needs terminals, storage, jetties, and carriers. Conversion needs cracking or electrolysis. Distribution needs pipelines, trucking, and barges. Bunkering needs maritime safety standards, terminals, and scheduling. No single molecule format can satisfy all of these roles cleanly. So the port treats hydrogen not as a single product, but as a portfolio. That portfolio approach is technically rational, but economically dangerous during the early years when utilization is low. If the port scales ammonia import capacity before local ammonia cracking demand matures, tanks sit underutilized. If cracking ramps before inland industrial contracts lock in, hydrogen sits waiting for offtake. If bunkering assets come online before maritime demand converts, terminals idle. If pipelines are built ahead of industrial conversion schedules, depreciation runs while volume stays thin. None of these individual mismatches are fatal. Ports routinely overbuild to attract business. The problem is that hydrogen infrastructure is capital intensive and faces brutal economics when utilization is low. A pipeline at 20% utilization is not a pipeline. It is a capital sink. A cracking plant running 4 days a week will not show bankable returns. A terminal sized for 2030 volumes will bleed if 2028 volumes show up at half the rate assumed in planning. Ports try to solve this uncertainty through redundancy. Redundancy is the enemy of bankability. It shows up in every layer of a hydrogen port: oversized tanks, oversized pipelines, oversized cracking, oversized electrical systems, and oversized safety infrastructure. It is motivated by a desire to avoid being blamed for bottlenecks in the future. If a major exporter shows up with 10 million tons and the port cannot handle it, the port loses business. Better to overbuild now and deal with the extra cost later. In conventional fossil industries, that logic worked. Fossil molecules had predictable demand, pricing systems, and geopolitical stability. Hydrogen is different. Demand is not guaranteed, timing is uncertain, and the pathway that wins ammonia, methanol, direct hydrogen, e-fuels is still being decided in the market. Overbuilding for every scenario becomes a strategy for losing in most of them. The port of Antwerp-Bruges exemplifies this tension. It wants to retain its position as an industrial gateway and protect its petrochemical ecosystem. Decarbonization threatens that ecosystem because emissions rules, carbon prices, and industrial competitiveness are shifting. If low-carbon molecules cannot be imported or produced cheaply, some industrial processes will relocate or shut down. The port is therefore betting on hydrogen as a replacement for fossil molecules, but it does not know which molecule format the market will settle on. So it builds infrastructure that can theoretically handle more than one format, and it lines up bilateral supply corridors with exporting regions. The corridors do not guarantee volume, they guarantee optionality. Optionality is strategically valuable but economically expensive during ramp-up. This is the point where electrolysis stops being the story. Electrolyzers are modular, learning curve-driven, and relatively easy to phase. They can be built in 10 to 200 megawatt increments and scaled over time based on price signals, power contracts, and offtake. The heavy parts of hydrogen ports cannot be scaled so easily. Terminals, tanks, substations, jetties, and pipelines are not modular. They are built in large, discrete chunks. Once in the ground or bolted to the quay, they need depreciation recovery, insurance, safety certification, and maintenance. If those assets are oversized relative to initial demand, utilization risk begins compounding through the balance of plant. And because hydrogen is a low-margin commodity in its early years, there is not much margin available to soak up that cost creep. Consider pipelines. They are the backbone of any hydrogen hub that serves industry and land. A pipeline is cheaper and safer than trucking or barging for large, steady volumes, but it is economically viable only at high utilization. Industrial hydrogen demand does not convert overnight. Steel plants, refineries, and chemical sites each have multi-year timelines for switching fuels or feedstocks. If a port builds a pipeline to serve 3 industrial clusters and only one converts within the first decade, the pipeline bleeds. If the port sizes the pipeline for 2035 volumes and 2030 volumes arrive at half the level predicted, the financial model tilts. If multiple ports build similar pipelines chasing similar hinterlands, demand fragments. Early winners preserve utilization. The rest carry stranded capacity. The same applies to cracking plants for ammonia imports. Cracking converts ammonia back into hydrogen and nitrogen. It is an energy-intensive process that requires capital infrastructure tied to utilities, safety systems, and logistics. If cracking capacity is built ahead of actual hydrogen demand, the plant runs below its design load factor. If it runs below load factor, unit cost rises. If unit cost rises, industrial customers delay conversion to hydrogen. When customers delay conversion, cracking stays underutilized. This becomes a feedback loop that reinforces the initial underutilization. And if cracking is paired with large storage capacity size for maritime import schedules, both assets must pay for that idle time through higher unit costs per kilogram. Ports know this risk, but they have another fear: missing the window. Hydrogen hubs will not be evenly distributed. It is unlikely that Europe will support 10 major hydrogen ports with global corridors and inland connections. The competitive map already shows clustering around the North Sea. If Antwerp-Bruges underbuilds, it risks losing the hydrogen gateway role to Rotterdam, Hamburg, Wilhelmshaven, or Dunkirk. Underbuilding risks industrial flight. Overbuilding risks financial drag. That is why ports choose overbuilding. It is a strategic hedge. But strategic hedges do not always convert into bankable projects. Bankability cares about volumes, timelines, counterparties, price formation, and utilization. Ports care about optionality, prestige, and long-term positioning. The two logics intersect awkwardly. Hydrogen exposes this awkwardness because hydrogen is not a silver bullet fuel. It is a conditional fuel. It competes with electrification, carbon capture, e-fuels, methanol, ammonia, natural gas with CCS, and even industrial relocation. If electricity becomes cheap enough, electrification beats hydrogen in many segments. If carbon capture becomes cheap enough, fossil molecules survive longer. If e-methanol wins maritime bunkering faster than expected, ammonia bunkering volumes lag. Each conditional future shifts the ideal infrastructure mix for a port. The port solves uncertainty by building for all futures at once. Investors solve uncertainty by waiting until one future becomes dominant. These timelines are incompatible. Add to that the brutal question of power. Electrolysis needs cheap renewable power. Ports have access to grids, but not necessarily cheap electrons. Ports can import hydrogen carriers like ammonia that embed foreign renewable power, but that means cracking infrastructure must compete with global ammonia prices. If renewable power in exporting countries falls faster than in Europe, imported ammonia becomes cheaper than local electrolysis. If imported ammonia becomes cheaper, domestic electrolysis stalls. If electrolysis stalls, the port's hydrogen production assets underutilize. Ports cannot control this dynamic. They can only adapt to it. This leads to the most important economic lesson of Antwerp-Bruges. The constraint is not electrolyzer CAPEX. The constraint is cost creep in the balance of plant and system design that surrounds hydrogen. Overdesign creeps into terminals, pipelines, bunkering systems, power substations, cracking plants, and storage. It shows up as redundancy, spare capacity, and multi-vector flexibility. It shows up as political hedging against uncertain futures. It shows up as insurance against industrial flight. It shows up as infrastructure that must be justified by future narrative rather than present utilization. The more optionality is purchased upfront, the heavier the all-in cost per kilogram in the early years. From a green hydrogen developer or investor perspective, this is a sobering frame. It means that large industrial ports cannot be treated as one-shot projects with binary outcomes. They must be treated as dynamic systems with sequencing logic. Sequencing logic asks one basic question: what must be built first to unlock utilization, and what can safely wait until volumes justify it? A staged port might build modest ammonia import capacity first, pair it with a single cracking unit sized for initial industrial demand, connect one inland industrial cluster, and defer bunkering until maritime adoption signals appear. The same port might defer multi-vector flexibility, methanol, e-fuels, liquid hydrogen, until timelines and price signals clarify. By staging the system, the port buys time, preserves capital, and lets market structure catch up. Ports that ignore sequencing tend to lose. They build for the movie they want to see rather than the reality unfolding. In this decade, reality favors narrow bandwidth projects with clear offtake and clear economics. It does not favor broad conceptual hubs designed for 2040 optionality. Developers and financiers increasingly want to know which molecules will flow, how much will flow, at what load factor into which industrial counterparty, and at what price. They do not care whether a port can handle every molecule imaginable. They care whether the first molecule pays for itself. Where does Antwerp-Bruges fit into this? It is still early in the story. The port has strong industrial logic, credible cluster links, and the physical infrastructure needed to become a hydrogen hub. It is well positioned geographically and institutionally. But its competitive advantage will not be decided by ambition or announcements. It will be decided by whether it can control overdesign and focus on utilization. If it builds for everything at once, it will raise dollar per kilogram and invite customers to shop elsewhere. If it sequences carefully, it can preserve its petrochemical role and attract hydrogen demand rather than chase it. This is where hydrogen professionals need a different toolkit. Ports and hubs do not fail dramatically. They fail quietly through underutilization. They fail through mistimed CAPEX. They fail through overly flexible designs that never justify their cost. They fail through long timelines that separate strategic intent from commercial execution. They fail through corridors that look global on a map, but remain notional in the real world. and they fail through financial assumptions that treat optionality as free when it is not. Professionals who work in hydrogen need to analyze these systems the way lenders, equity partners, and industrial buyers do, by modeling utilization, cash flow, offtake, and price formation under stress. That is exactly why we built H2 Hub by Renewable Energy, because the market is shifting from enthusiasm to bankability. Hydrogen is leaving the era of slide decks and entering the era of underwriting. Hubs will still be built, but they will be built by numbers, not narratives. Antwerp-Bruges may yet become a defining hydrogen port. Whether it does or not will hinge on the part of the system that no slide highlights, the quiet drag of overdesign that kills dollar per kilogram long before final investment decision. If you're in the business of helping hydrogen projects reach bankability, whether as a developer, consultant, strategic buyer, or investor, you cannot treat ports as abstractions. You need to model them the way capital markets will, by sequencing, utilization, and conditional futures. Ports are the hardest place for hydrogen to hide. They reveal cost structure without mercy,